Okay, so we're going to do a topology optimization of a bracket. So the first thing we want to do is create a new part and draw the 3D model that is there given in the write-up. So just a quick recap. You go to Sketch, click on New Sketch here and whatever plane you want to start. So you will select the top plane and then we will draw the profile of the part we want to draw. So we have our sketch here. Alright, this here is 1501515. I don't know why SolidWorks is now given overlapping the 1 and the 5, but essentially is 150, 15, 15, 15, 15, 15. Alright, so now what we could do, we can exit the sketch. Then we go to features and then we could extrude. And our extrude thickness is 10 millimeters, so that is good here, and you can select that. So now we have our part, our component. Alright, so remember at this point to save. And when you save to a folder on your desktop. And we can call it Alright, so now we could perform the analysis. For this, we go to simulation. Again, if you don't have simulation shown here, you go on top here and you select one of these here. One like here will be professional, you would have. And wait some time and then you would see simulation. And the first thing we want to do is a static study. Right, we just want to get a feel of the stress in it, so we click new study. Right, so make sure static is selected here, click OK. And then we could go to the same procedure as we did for the previous examples or the previous class activities we did. Material, apply edit. So we want 6061 aluminum. So for that we collapse steel, we look for aluminum alloys and we look for 6061. 6061 alloy, apply. Then we close. So the material for the bracket is that. Next we want to put some constraints. So we're saying that this is bolted. So this will be more or less like a hinge joint, these two holes. So we could go on fixtures, fixed hinge. Right, so you could see it permits rotation. So we can select the inside faces. Right, ensure that the two faces are selected and then OK. So now we have our fixed hinge. The next step is to apply a load on top here, and the load was 1 megapascal. So we go on external load, we apply a pressure. Right, this is our face here. Actually, the arrow is pointing correct already, so it's 1 megapascal, so it's 1 e to the power 6. Okay. Right, so we have defined our materials, we define our boundary conditions, we applied our loads. The next step is the mesh. So we right click, create mesh. Right, and that is good here in the middle and OK. So you can see our mesh has been generated. Right, so before we run, we can click save. Just to ensure that if it crashes, we have our model. And now we could right click static, run. Right, so here we see our analysis here. So the yield strength of our material is 55 megapascals. Right, and you can see here that we are below that in terms of our von Mises stresses. Right, we could see our regions of stresses around the holes, on top, below, and this dark region here, we are saying that the stress is really low. So we do not really need all this material in here. So we're going to ask the software to do topology optimization, meaning that we're going to manipulate the topology of this part such that it could maintain the safety of the part but with less mass or with less material. Right, so that is what we're going to do now. Right, so we're going to do a topology optimization. So instead of having to specify all these things again, material, boundary conditions, load, etc., we could copy this analysis. Just copy this model, what we have done here. So on the bottom here, we have static. We right click and say copy study. So it would ask what is the target study. We can do another static analysis with different loads if you want, but we want to do topology. So we will click on topology optimization or topology study. And then you will see the name will be topology study, and it's based from static one, meaning that the same material, same boundary conditions, etc. And we can click the tick mark here. Right, so under the topology, you will see some things that are different, that are new here. So here we have goals and constraints, manufacturing control. So these are two different or two new things. And the goals and constraints here is what we discussed, meaning that what is our goal, what is our intention? And our intention in this case is to reduce the mass. Right, so what we want to do, we could click minimize mass here. So that will means that it will get the lowest possible mass. But we could also select minimize the maximum displacement if it is we want it to not deflect too much. Or we could also look at best stiffness to weight ratio, and you can see that this is the default. And it's the default because, as we know, and we did in design, stiffness to weight is something that we look to want, or strength to weight. Right, so it gives the best ratio, the most appropriate ratio. Right, so we will click on, we keep it default, keep best stiffness to weight. Right, and what we want to do, we want to constrain the mass. So our goal is to get the best ratio, right? But what we want to do, we want to constrain the mass. So it will try to get the best stiffness to weight ratio, but at the same time, it will try and give you, okay, a reduction in the mass. So we want to reduce our mass by, say, 30%. So we could see here our current mass is 0.166 kilograms. And with this 30%, it will be reduced to 0.11 or 0.12. So you could see here in the aviation industry or the aerospace industry, where topology optimization is of utmost importance, because at the end of the day we want to maintain mass, but at the same time maintain our strength and our ratios, our stiffness ratios. Alright, so we will keep it at 30% for now, and we'll click the green tick here. Alright, so the next step here is manufacturing controls. So if you click on manufacturing, right click manufacturing controls, you will see a number of options here. So the first thing I'm going to go to here is add preserved region. Right, and what preserved region, what this means is that we said that SolidWorks is going to remove material from this. So we want to specify regions where that we may not want it to remove material from. So automatically SolidWorks recognizes that this is a boundary condition, here is a boundary condition, and we have the load on top. So SolidWorks of course will not remove material from on top because that is where we need the load to be. Right? So if it is we want to go further in that and we say, okay, we don't want material removed from this tip here, well then we could specify that if we want. Alright, so we can click add preserve region. So we could say, okay, we want to preserve material around the holes. Now, SolidWorks will already preserve some, but let's say we want to have more control. So we click preserve area depth, and we could say, okay, let's reserve, or let's make sure SolidWorks keeps 10 millimeters around that. We can see how it will look by clicking geometry preview. So this is how that would look. If it is, we say, okay, we want to preserve 10 millimeters around it. Right, so that means that it will remove material, but it will keep this amount of material right around. We could decrease it to 5, and it will look like this. So it will keep this amount of material right around the holes. Right, so we could go with 10. If it is there's no issue with the back here. If it is we want the front to remain, we could click that there. We could add another one, preserve region. So we could click this face here, and we could say, okay, we want 5 millimeters. So what it will do, it will keep 5 millimeters of material there. Or it will ensure that 5 millimeters at least remain. Right, so that is what preserve region could do, right? So I'll X that off because we're only concerned with the holes here. And we establish that SolidWorks will keep material on top here automatically. The next I want to go into here is specify demold direction. So I'll click on that here so we could see this graphic here. Right, so what this is specifies how we want the material to be removed, depending on the type of part we have. Right, so there's things manufacturing like injection molding, for example, where we may need to keep the back solid, but the inside alone here remove. So for example, the back of this little bracket here in the animation will be solid, but we only be moving material up to a certain point. Right? In our case, we want a stamping pull, meaning that we want it to go straight through. Right? There's no issue with it needing to have material in the back. Right? And in that select pull direction, we would click this corner here to say that that is the direction in which we want the stamping to happen. Right? So that's good enough there. We could click the arrow. So we tell in SolidWorks that you could remove material, but you could remove the material straight through the surface or through the plane, this plane of the material, down into the screen. Right, you could also add specified thickness control. So that is something similar to preserve region. So you could actually say, okay, you want to maintain the thickness below here, but there's no need to maintain the thickness of this region, for example, right? The next thing here is specify symmetry planes. Now, if you look at this part, we have symmetry down the cross section here, right? So there's no need for SolidWorks to analyze this half and this half. It's like giving it double work. We established already that we want the holes or the material to be removed. We want a stamping operation where it goes straight through. Right, so it will be symmetric about the middle plane of this part. So what we could do, we could right click, create a symmetry plane, and tell SolidWorks that the bracket is symmetric about that plane. Right, so before we do that, we need to create a plane in the middle here. Alright, so to do that, to create this plane, we go to model on the bottom here. So go back to the modeling page where we would do drawings and stuff. We go to features, and you would see here reference geometry. We can click on it and click plane because we want to create a plane. Alright, so we want a plane to be in the midway between this plate here. So we could click this surface here, and we could say, okay, we want it to be halfway. Well, we know halfway is 5 millimeters deep. It already has 5 millimeters here, so we can click flip offset. So you could see here the plane is in the middle. Right, so we tell in SolidWorks we want the topology optimization calculation to happen on one side, which is less elements, so the process will happen faster. And whatever results we get here obviously will be the same on the other side. So that's what symmetry means. Right, so we create the plane there, we click this tick. So we have plane 1 as you see there. So now we could go back to topology study. Right, click manufacturing control, specify symmetry plane. And we're looking at half symmetry. So we can click on the plane here now. And okay. Right, so we created a half plane symmetry. Right, so the next thing or the last thing before we run the model is to create mesh. Right, so a bit coarser, we could put it up a little. So we created the mesh here. Right, so depending on your computer you're using, it might not be able to go too fine because this takes a long time to run. So what I'll do now, at this point, we could click save before we do any running of the model. Right, so now we could click on topology, study here, right click and click run. Right, so it will start to run. Right, so what it does is it keeps running different iterations. So it will solve the model, remove material, solve the model, remove material, and it'll keep doing that until we have some type of convergence happening where removing material does not give any benefit. Right, so this will take some time to run. Right, so I'll pause and come back to it at the end. Right, so after some time, you would see the view convergence data will show up this graph. So you can click on these graphs and you could actually see, like for example, the mass, the target mass we said was 0.1623, right? So we can click on it and we could see here that it actually almost reaches the target mass, right? Iteration means every time it runs the model, right? We can click on best stiffness, meaning that you can see this goes down, so it's going towards that goal, right? The goal here being the change from um, ratio to ratio. Remember when we did convergence? So that is what it's doing here. Right, so we'll go until it reaches our acceptable tolerance, meaning that the change is so small that small change is acceptable for it to say, okay, we could stop the solution, we are happy with the solution. Right, so this is the model, this is the topology optimization completed, being completed here. Right, so you could see that we have preserved 10 millimeters around the hole, so that's why you see in this large area here being preserved. And you can see also it removed areas of material that is deemed not required. Right, so the mass has been reduced by 30%, but the load bearing capacity of it has remained the same. Right, the legend on the side here goes to show that what must be kept, obviously the green here must be kept, and what can be removed. So the blue could be removed. Right, so how do we now, what do we do with this? Because you can see it's all jagged and all that, so we need to clean this up. So one way to do it is to right click and we can export smooth mesh here. Right, so that's one way we could look at. And what that will do, that will create something called an STL file, which is suitable for 3D printing. Right, but when we do that, it will still be jagged. I will just right. So export smooth mesh. We can click on new part file. This is where we want to save it, and so a new part file is supposed to be saved here. So we can look at it. Okay, so exporting the mesh body is not working on my SolidWorks here. Right, but essentially you do exported mesh. You could do new part file. You select a name, save file to, and okay, and that will create a mesh file. Right, but essentially what that will do, that will create a body with jagged edges like this. So unless you want to probably 3D print this thing, and even so if you want to 3D print it, you want it to be a lot neater than this. Right, so what we could do now is use some of the tools that we are custom using in SolidWorks, your drawing tools, so we could draw over this. So that way we could physically cut out the material that the analysis is saying that we could cut out. So for this, we'll again ensure that we save. We can go back to model. Right, so this was our original model. Now keep in mind now that when we do this, we're going to overwrite this model. Right, so we can click up here, simulation display, and there are a number of simulation results that we could show. We actually want, from the topology study, we want that material mass reduction model. Right, so this is the model that we want. So we can click OK. Right, so what we do now, we have just overlapped that simulation results with the geometry or the model that we had drawn initially. Right, so what we could do now, we could actually draw now or trace over these holes or these cutouts. Right, so for that we could go features or we could go sketch. We can define a sketch on our plane here, our front plane. Right, so be careful not to select plane one that is the middle, but select the middle plane here. I'm sorry, the top plane here. And now we could actually start sketching. Right, so you could grab a line, for example, and Right, so we could draw this line here, and then what we will do now, we have created a profile where we could cut out from the material. Now keep in mind that if it is we want to machine this part, these vertices must be at a radii that would allow machining. Right? If it is, let's say this the radii is using a tool that is 5 millimeters in diameter, obviously it cannot go into here, so you end up with a curved edge. Right? So you could specify all those things. You could specify a fillet radius, select the and we could put a fillet radius of 3 millimeters. That's so that's a bit big. Right? So we can do things like that to smooth out and make the model or make the geometry a little more realistic. Right, so we could continue that for the different components here. So right, so after you draw it, yeah, you could actually grab the line and bring it out a little more if you want. So remember, we're not really supposed to go into the green spaces here. Right, so I'll continue this and we will see at the end. Right, so you can see here I drew profiles to kind of mimic. Right, so you would be a lot more neater, of course, when you're doing your projects and stuff. Right, this is just for demonstration purposes. Right, so I still have one here. Right, so for the end here, we could just draw a line to represent that curve here. Now, if you want to be a little more on point, instead of drawing a line here, so you could see a line here, what we be doing, when we cut this out, we still having a lot of material that will remain here. So what we could do, instead of doing a line, we could actually do a spline. Right, so we actually did a spline here now. That a little closer, we could drag some of these points here if you want. That's the nice thing about working with splines, to bring it in a little more. Right, so now that we have done that, we could exit the sketch. Right, and then we go back to features, and we go to extruded cut. And this is where we could select now all our profiles we just made. Right, so this spline is not creating a close point, so we have to go back into the sketch and create a closed loop here. Right, so when you zoom in, you realize that the point was not on the line. You can just drag it and ensure that it's on the line, coincident with the line. Ensure that the same constraint is here. Good. So now it's supposed to work. Right, so you can see it was able to be selected now. Right, so remember we are extruded cut, so it's 10 millimeters a cut through. That's the entire thickness. Right, so you can see here we did the cuts. So over here now we could go back to, we can take off simulation display. So you can see we left with our solid bracket here. Right, so this is the bracket. Now it wouldn't be exact 30% less in weight because remember we drew those lines not at the exact point in which the material was removed, but essentially we were able to remove some material. Right, so the closer here, the more we find you do over the analysis, you do to 40%, you do 50, 60, then you reach a point where you can really see how thin the material could be and how much useless material you could actually remove. Right, so you ensure that you can save. Right, so now what we would like to do now is to run this model again to ensure that everything is safe then. Right, so we could go back now and do our static here. Click on static, and you can see the model, of course, has been updated to static. So that is why I said that it changes permanently. Right, so we go back to static here, so you can see it updated, and then we could right click and run the static model again. Right, so you could see now the updated stress analysis of it. Right, so before it didn't have no high stress points over here. That's because it was a solid blue. But because now we have material removed here scenes, but it's not failure stress. Right, so we're making a better use of the material then. Right, so you can still see it's still below the yield shrink. Right, so that is topology optimization in SolidWorks. And I urge you all to watch the 2 YouTube videos that are on the lecture notes as they go more in depth, especially longer video, goes more in depth in terms of using all the tools and explaining some of the tools a little more in depth than I did. Right, so thank you all for watching.